All right, let's get into it. Today, we're going to pull back the curtain on computer science. Seriously, we are going to take a journey that starts with a tiny, little on-off switch and ends with, well, the entire internet.
And you know what? Let's be honest. Most of the time, they really do feel like that. This box on your desk, it's like a magic portal to the entire world. But here's the secret. It's not magic at all. It's just logic stacked in incredibly clever layers. And we're going to unpack those layers right now.
So, everything, and I mean everything a computer does, starts right here with the bit. Deep inside your computer's processor are billions of microscopic switches. They're called transistors, and each one can only do two things: be on or be off, a 1 or a 0. That's it. That simple binary idea is the bedrock for everything else.
So, the big question is, how in the world do we get from a simple on or off switch to storing, every cat video and encyclopedia article in existence? I mean, one switch by itself isn't very useful, right? But when you start grouping them together, that's when their power just grows exponentially.
So we take 8 of those bits and we bundle them together. We call that a byte. And suddenly, with just those 8 little switches, you now have 256 different possible combinations of ones and zeros. This lets us represent numbers using a system called binary. Each spot in the byte is a power of 2. And just like that, those simple on-off switches can count all the way from 0 to 255.
And this isn't just for numbers. We came up with these brilliant systems like ASCII. Think of it like a universal dictionary for computers. It gives a unique number, a specific pattern of ones and zeros to every single letter and every symbol. So when you type the letter A on your keyboard, the computer has no idea what an A is. It just sees 01000001.
Okay, so we can store information now. But how does a computer actually do anything with it? How does it think? How does it calculate? Well, this is where the hardware really gets to show off.
You've got to understand the partnership between the CPU and RAM. The CPU is the brain. It's an absolute genius at following instructions. But it has a terrible, terrible memory. It can't hold on to anything by itself. That's where RAM comes in. RAM is the super-fast temporary workspace. It holds all the data and the instructions that the CPU needs, like right this second.
And to get anything done, the CPU is constantly doing this little 4-step dance. It fetches an instruction from RAM, it decodes it to figure out what to do, it executes the command, and then it stores the result right back into RAM. Fetch, decode, execute, store. Over and over, billions of times, every single second. All kept in perfect rhythm by an internal clock. It's just this incredibly fast and efficient loop.
Okay, so obviously typing out billions of ones and zeros by hand would be completely impossible. Not to mention just mind-numbingly boring, right? So we needed a better way to talk to computers. Something a little more human.
And that bridge between us and the machine, it's a concept called abstraction. It's maybe the most important idea in all of computer science. It lets us write instructions in a language that we can actually read, like print, "Hello World." Then a special program, a compiler or an interpreter, does the hard work of translating that simple command into the thousands of ones and zeros the computer actually understands.
And different languages do this translation in different ways. You've got interpreted languages like Python, which basically translate your code on the fly, one line at a time as it's running. Then you've got compiled languages like C, which do all the translation work up front. They create one big file that the CPU can run directly, which is usually way faster.
But how do programs keep all this information straight? I mean, just throwing data into one big messy pile would make any program grind to a halt. We need clever ways to organize it, to structure it.
And these organizational methods are called data structures. The best way to think about them is like different toolboxes for your data. You wouldn't use a sledgehammer to fix a watch, right? Same deal in programming. You have to pick the right data structure for the job, and each one has its own specific strengths and weaknesses.
This shows a classic trade-off. An array, on one hand, is like a numbered row of parking spots in a garage. It's blazingly fast to jump straight to spot number 75. But you can't easily add more spots. A linked list, on the other hand, is more like a scavenger hunt. Each item just points you to where the next one is hidden. It's super flexible. You can add or remove items easily. But if you want to find the 100th item, you got to visit the 99 before it first.
Now this is just a perfect analogy. The stack data structure is so simple but so powerful. Whatever you put on last is the very first thing you take off. Last in, first out. Simple as that.
This is actually fundamental to how your computer manages programs when they're running. And right here, we're seeing an algorithm in action. An algorithm is just a fancy word for a set of rules to solve a problem. With a sorted data structure like this binary search tree, you can find any number you're looking for incredibly fast. You just start at the top and keep asking, is my number bigger or smaller? You cut the number of things to search in half with every single step.
All right, it's time for the final layer. How do we take all these individual computers with their CPUs and their data structures and connect them all into one single global network? How does the internet actually work?
Well, here's the thing. The internet isn't some magical cloud floating in the sky. It's a very real, very physical network of wires and cables, many of them running along the bottom of the ocean, connecting computers all over the world. Every device gets its own unique address, an IP address. And when you send something, your data gets chopped up into these tiny pieces called packets. Think of them like digital postcards to make the journey.
So every single time you go to a website, this lightning-fast conversation happens. Your browser is the client. First, it looks up the website's IP address in the internet's giant phone book, which is called the DNS. Then, it sends a request to that address, saying, hey, can I have the web page? And the server on the other end, the computer that hosts the website, responds by sending back all the files needed to display it. All of that happens in the blink of an eye.
And where is that server getting all its information? Almost always, it's from a database. Most of the world's data is organized in what are called relational databases. You can just picture giant interconnected spreadsheets. And they use a special language called SQL to manage all of it, from your user account to an entire store's inventory. But here's the catch. Because everything is connected, and everything follows these very specific, predictable rules, it can also be vulnerable. This string of characters here, it looks like random gibberish, but it is not random at all. It's actually a key designed to break into a poorly secured system.
See, by cleverly typing this into a username box, an attacker can completely change the instructions the database receives. The logic flips from check if this password is correct to log me in if the username is blank or if 1 equals 1. Well, guess what? 1 always equals 1, so the database just lets them in. It's called an SQL injection, and it's a perfect example of how knowing the rules of one layer can let you break the rules of another. It's why security is so incredibly important at every single step.
So think about it. We went from a single switch that can only be on or off all the way to a global network just by building clever layer of abstraction on top of clever layer of abstraction. Each new layer lets us forget about the complexity below it and build even more amazing things on top. It really makes you wonder, what's the next layer going to be?